France, mid-1950s. An engineer named René Leduc is building something completely wild, an experimental interceptor with a combined propulsion system. This was a prototype fighter for the French Air Force. What made it special? It had two engines running at the same time. A conventional SNECMA Atar 101D3 turbojet for takeoff and low-speed maneuvering, and Leduc's own ramjet for supersonic flight. That combination meant the aircraft could take off from a regular runway under its own power. Earlier models had to be dropped from carrier aircraft up in the air. Not exactly practical. The fuselage itself looked unusual too. Double wall construction specifically to house the ramjet's combustion chamber, swept wings at a 30-degree angle, and an escape capsule for the pilot that fired off as a complete unit. Leduc had been working on that technology since the 1930s. The aircraft grew out of earlier prototypes, the 0.10 and the 0.21. Testing began in 1956. That same year, the French military was actively looking for a new high-performance interceptor. The first flight took place on December 26th. They flew exclusively on the turbojet. The ramjet was successfully ignited for the first time on May 18, 1957. By December, the prototype had pushed past Mach 1.15. That proved something specific. Manned ramjet-powered aircraft were a realistic option for military use. On armament, the plan was to carry two Nord AA-20 air-to-air missiles, or 24 unguided rockets. The aircraft's role was narrow. It was a short-range interceptor designed to climb as fast as possible to 8,800 meters. A few numbers to get a sense of the size. Length, 18.21 meters. Wingspan just under 10 meters. Maximum takeoff weight approaching 9 tons with fuel capacity of 2,728 liters. The ramjet produced 63.6 kilonewtons of thrust at 1,000 kilometers per hour. Impressive. Over 140 flights went off without a major incident. Sounds great, right? Sure. But the problems were serious. The program was plagued by severe aerodynamic drag. And during ground tests, shortly after that supersonic milestone, the prototype caught fire. In February 1958, the French government shut the program down. Assembly of the second prototype was canceled outright. The reason was straightforward: severe military budget cuts. On top of that, the military had already set its sights on more conventional turbojets like the Dassault Mirage III. The Mirage was cheaper and could handle a wider range of missions. The fire-damaged Leduc 0.22 was eventually repaired. It now stands at the Air and Space Museum in Paris, a physical reminder of France's experiments with supersonic flight and of just how risky it was to push alternative propulsion during the Cold War. René Leduc worked as an engineer at Breguet Aviation. Sometime in the early 1930s, he started experimenting with ramjet engines. In 1933, he secured a small government grant to pursue the idea. 2 years later, he had a working prototype that produced 4 kilograms of thrust. Sounds laughable, sure, but it proved the core concept. Air could be compressed for flight at high speeds without any mechanical compressors. It's worth understanding why the idea seemed so attractive in the first place. A standard turbojet is a complicated machine. Compressor, turbine, combustion chamber, hundreds of moving parts, any one of which can fail. Maintenance was expensive and time-consuming. A ramjet, by comparison, is just a tube. Literally, no rotating parts at all. The airflow itself provides compression, fuel burns inside, gases exit through the nozzle. That's the whole design. Simpler means more reliable. That was the argument Leduc was selling to the military and government officials going all the way back to before the war. There's another angle that doesn't get talked about much. Leduc wasn't a typical academic engineer. He didn't hold a university chair and didn't write thick technical reports for the ministry. He built things. He pursued this obsessively on his own money, then on small grants, then on his own again. French bureaucracy dragged its feet on funding for years, and Leduc kept the program alive by giving lectures, consulting, taking any work he could get. Without that kind of personal stubbornness, none of these aircraft would have existed. Then came 1939, World War II. The Germans occupied France. Leduc hid all his blueprints to keep them from being stolen. After the war, money was desperately scarce. Progress was slow, but those early steps had put France in a leading position in this technology, right when it mattered. The Cold War was starting, and the military urgently needed high-speed interceptors to counter Soviet bombers. Back in 1938, Leduc had already conceived the 0.10. Initially, it was just a glider for proof-of-concept testing, but on April 21st, 1949, it did something no aircraft had ever done before. It became the first manned airplane in history to fly solely on ramjet power. It was air-launched from a carrier aircraft, a Sud-Est Languedoc. That scaled-down aircraft reached 805 kilometers per hour. It showed the concept worked in practice. The 0.16 and 0.21 versions followed. By 1953, they had improved high-altitude performance and were reaching Mach 0.87. The success of the original 0.10 proved that ramjets were ideal for cruising at supersonic speeds. There was just one problem. At low speeds, they produced no thrust at all. The aircraft absolutely needed a conventional engine to accelerate it up to operating speed. And that problem defined how the next generation of combat interceptors would be built. 1953. The French Air Force issues new requirements. They need a high-speed, short-range interceptor, speed exceeding Mach 2, takeoff from unprepared strips shorter than 1 kilometer. The primary job? Climb fast and shoot down the enemy. France needed to close the gap with the British and Americans in jet aviation. Those requirements directly influenced the Leduc 0.21 as a research baseline, and eventually its successor, the 0.22. Here, the engineers used a very clever approach. They placed a conventional SNECMA Atar turbojet directly inside the ramjet duct, coaxially. Why? The turbojet handled takeoff, taxiing, and acceleration up to the speed at which the ramjet could ignite. Then, the ramjet took over for the supersonic push. Nothing protruding on the outside. Minimum aerodynamic drag. It should be said, the French didn't invent this hybrid approach from scratch. They drew on European experience, specifically German wartime developments, the V1 and Messerschmitt projects, and used those as a foundation for their own new light air defense systems. It all started in 1953. The French Ministry of Defense contracts Leduc's firm to build a new interceptor, ramjet-powered, and the critical requirement, it had to take off under its own power. Construction began in 1954. The next 2 years went into assembling the airframe and engines. By 1956, the aircraft was ready, and that same year, the first ground runs began. Money was extremely tight after the war, so the military program funded only a single prototype. The predecessor, the Leduc 0.21, had launched from a carrier aircraft in the air. The new 0.22 had to take off from the ground on its own. Fitting coaxial turbojet and ramjet engines into a compact fuselage turned out to be a serious engineering challenge. The engineers had to measure every duct millimeter by millimeter. Airflow had to be smooth, and the structure had to hold together at supersonic speeds. The ramjet inlet was built from stainless steel. Anything else would have melted from the temperatures generated during supersonic combustion. The Atar 101D turbojet for low-speed operation came from SNECMA. Leduc's team was focused on the outer duct. The ramjet was developed based on their previous research. Late in 1956, the turbojet was successfully tested on the ground in a static run. They were ready to prepare for actual flight. This was a tailless delta with a swept wing. Leading edge sweep angle, 30 degrees. Wingspan just under 10 meters. Length 18.2 meters. Wing area was 22.1 square meters. Why that geometry? To cut aerodynamic drag to the minimum. The aircraft had to operate reliably above Mach 1 without breaking apart from aerodynamic loads. The fuselage had double walls. It essentially was the ramjet's combustion chamber. The pilot sat far forward, right inside the intake cone. The nose was designed to capture maximum airflow. The nozzle sat at the very tail for a direct thrust vector. This saved weight and gave the aircraft a perfectly clean profile for transonic and supersonic speeds. No unnecessary protrusions anywhere. The aircraft was controlled by elevons on the trailing edge of the wings. They handled both pitch and roll. No separate stabilizers. No vertical fin either. Why? Because the engine fuselage couldn't tolerate any superstructure. Those would have broken up the airflow and generated parasitic drag. Skin and frame were aluminum. Where loads were extreme, the engine and landing gear attachments, steel was used. Notably, this was the first aircraft in France to use titanium. That combination of materials kept the aircraft light enough to take off from a 940-meter dirt strip. For the military, that was critical in a wartime scenario. When bases get bombed and aircraft have to be dispersed across open fields. The engineers kept things simple by essentially embedding the propulsion system directly in the fuselage structure. The propulsion system in the Leduc 0.22 was hybrid, coaxial. The SNECMA Atar 101D3 turbojet was placed inside the much larger ramjet. That finally allowed the aircraft to take off on its own. The smaller turbojet produced 31.3 kilonewtons of thrust, enough for taxiing and the takeoff roll. The ramjet was designed to generate 63.6 kilonewtons at 1,000 kilometers per hour. The smaller engine's nozzle sat at the center of the larger one. What did that give in practice? The turbojet functioned as both a starter and an ignition source for the ramjet. No external assistance was needed for startup. How does a ramjet actually work? Air is compressed simply by the aircraft's forward motion. This kind of system generally starts working above Mach 0.8. Air enters the inlet duct and slows down. Pressure builds up. No turbines or compressors involved, just a tube. Fuel is injected into that compressed air, it combusts, expands through the nozzle, and you have thrust. The mixture was ignited by hot exhaust gases from the running turbojet. That guaranteed a reliable light-off the moment the aircraft reached the required speed. The design is about as clean and logical as you can get for supersonic speeds. Conventional turbojets at those conditions often suffer from compressor stall. With a ramjet, that problem simply doesn't exist. The transition between engines worked like this. The aircraft takes off on the turbojet, accelerates to around 300 to 400 kilometers per hour. At that point, the ramjet ignites off the exhaust. For a time, both engines run together. Once speed reached roughly Mach 1, the smaller engine was shut down. That saved fuel and the aircraft flew supersonically on ramjet thrust alone. The fuel system used wing tanks holding 2,728 liters of kerosene. Sounds like a lot, but that was only enough for 10 to 15 minutes of high-speed flight. Where the pilot sat is its own story. In the nose cone, literally inside the air intake. In front of him, a glass canopy and nothing else. No side-hinging exit. Leduc had been developing an ejectable escape capsule since the early prototypes, an entire nose section that blasted away from the fuselage with the pilot still inside. At high speeds, conventional ejection is simply impossible. The airflow would instantly kill a person, so the capsule flew off as a separate projectile, then a parachute deployed. Sounds terrifying, but at the time it was a sensible engineering solution. Leduc had thought about this from the very beginning, back when he was developing unmanned models in the 1930s. The pilots who flew the 0.22 voluntarily accepted that emergency procedure. Test aviation in those years was a business for people with an unusual relationship with risk. But even among them, Leduc's nose cone was considered a particularly specific place to work. You're sitting essentially inside the engine, fuel burning around you, nozzle behind you, and the only way out alive in a crisis is to blast yourself forward in a chunk of airframe. Testing of the Leduc 0.22 began on December 26, 1956, at Cazaux Airfield. The first flight ran exclusively on the turbojet, and that was a genuinely significant step forward. Every previous Leduc prototype had to be carried aloft on the back of a carrier aircraft. The program moved quickly. Over the course of 1957, they completed more than 140 flights. Most of the flying was done at Cazaux and Istres. The French Air Force was taking this aircraft seriously as a potential interceptor. On May 18, 1957, during the 34th flight, the ramjet was ignited for the first time. Combined thrust testing had begun. And on December 19th, the aircraft went supersonic, reaching Mach 1.15. 2 days later, it was over. On December 21st, 1957, the prototype caught fire during a routine ground run and was completely destroyed. Those flights had exposed a pile of real problems with the ramjet design. Transonic speeds produced severe vibrations that threatened the structural integrity of the airframe. At high speed, the cockpit canopy overheated badly, and fuel consumption was so enormous that the flight endurance turned out to be critically short. All that data was collected and passed on to the French military. Mach 1.15. That's roughly 1,200 kilometers per hour. That's the speed the Leduc 0.22 achieved during testing when it lit the ramjet. Operational ceiling was 8,800 meters. The supplementary turbojet provided a climb rate of 30 meters per second, more than enough for intercepting targets. All those numbers were confirmed in actual flight. The hybrid propulsion system genuinely worked supersonically. What was the key selling point of the design? The violent acceleration once the ramjet lit. The aircraft would climb steadily on turbojet thrust, then switch to the main engine and instantly surge toward high speed. On top of that, it could take off from short, totally unprepared dirt strips. For point air defense in the mid-1950s, that looked like an ideal solution. But there was one enormous problem: 20 minutes. That's exactly how long this aircraft could stay airborne. The ramjet burned fuel at a ferocious rate, so any kind of sustained patrol or waiting on a target was completely out of the question. Takeoff, strike, land, or crash. On top of that, the moment speed crossed Mach 1, controllability became chaotic. The pilot had to constantly fight the aircraft just to keep it from being flipped by aerodynamic drag. Any serious maneuvering was out of the picture. You have to understand the context of what was happening in aviation in the late 1950s. The main threat to the West was Soviet strategic bombers. The Tu-4, then the Tu-95, then the M4, a large, slow target at high altitude. That was the exact scenario the interceptors of that generation were designed for. Climb fast, reach altitude fast, fire missiles, return. Maneuverability was secondary in that equation, so the Leduc 0.22 was initially taken seriously. If this aircraft executes that one specific algorithm faster than the competition, why does anything else matter? Test pilots described the switch to ramjet mode as a hard shove in the back. Not a smooth acceleration, a shove. The turbojet drones steadily, and then suddenly something completely different opens up from behind. The sound changed in character, deeper, broader, felt throughout the entire fuselage. At the same time, handling immediately became heavier. The aircraft surged toward speed, and the ailerons responded with a lag. Pilots said that at Mach 1, the aircraft started living its own life. The military initially considered it seriously as a short-range interceptor. It had the speed, it launched instantly. Then the Dassault Mirage III walked onto the stage. A normal multi-role jet fighter, it could fly long missions, handle a variety of tasks, and didn't try to kill its pilot at supersonic speeds. Against the Mirage, the Leduc 0.22 suddenly became irrelevant. The program was shut down in early 1958. They had completed around 140 flights. Well, shut down, what actually happened was that in December 1957, the first prototype burned up during ground testing. Nobody wanted to restore it. The second prototype was slightly luckier, although it never flew a single flight. It sat unfinished for years until 1979, when the Leduc family donated it to the Air and Space Museum at Le Bourget. It's still there. The aircraft stands in Paris as a static exhibit. It was deliberately left without restoration, and the structure remains in its original condition. Even the old instruments in the cockpit are still in place. It will never be returned to flying condition, of course. That technology is long dead, but if you ever visit the museum, you can see it in person. It stands alongside its predecessor, the Leduc 0.10, a strange branch of French aviation that simply ran into a dead end. If you stand next to this aircraft in the museum and look at it without any background knowledge, it just looks odd. Too elongated, nose too sharp, wings cut at a strange angle. No resemblance to conventional jet aircraft of that era. But that's exactly the point. This wasn't a side branch off some larger mainstream project. This was one man who conceived a principle in the 1930s and spent 20 years trying to prove it. And in a certain sense he did, even at the cost of the project itself. Leduc never built anything else after the program was shut down. The company was dissolved. He died in 1968. Most of his colleagues went on to large aerospace firms, Sud Aviation, Dassault. The people who had worked on the aerodynamics of the 0.22 later contributed to Concorde. The skills developed on ramjet programs, inlet calculations, thermal protection, airflow behavior at transonic conditions, turned out to be directly applicable. The Leduc 0.22 proved that combined engine propulsion was feasible. How did it work? Engineers simply placed a conventional SNECMA Atar 101D turbojet inside the larger ramjet. That allowed the aircraft to take off on its own. Then, already at altitude, switch to ramjet mode. The French later applied that experience when developing their own missiles. In 1958, the program was wound down. France urgently needed multi-role fighters meeting NATO standards, so the military chose the Dassault Mirage. The Leduc project stopped, but the data collected didn't go anywhere. Researchers spent years going through the flight test records to understand exactly how airflows behave at supersonic speeds. That idea of combining two engine types was significantly ahead of its time. A single propulsion system accelerating an aircraft from conventional to supersonic speeds. Where is it used today? In hypersonic aviation. The modern French PROMETHEE project, being developed for flight speeds between Mach 2 and Mach 8, is technically built on those same principles. All the test results from the Leduc 0.22 now sit in the archives of France's Aerospace Research Institute, ONERA. And here's the most interesting part. Engineers in the 21st century still read and cite them, especially when modeling combustion processes for new ramjet systems. If you step back and look at the bigger picture, the Leduc 0.22 was one of the very few projects of its era where a hybrid propulsion system actually made it to real flight testing. Most competitors stalled at the bench test stage or never got off paper at all. The French went further. They collected a solid body of numbers: airflow rates, temperature profiles inside the duct, combustion stability across different operating regimes. Those numbers later formed the basis for calculations used in French ramjet-powered anti-ship missiles, the ones that eventually evolved into the ASMP family. There's a certain irony in all of this. The program was shut down just as it was starting to deliver real results. First supersonic flight, December 1957. Fire and loss of the prototype, that same December. Program officially closed, February 1958. Between the first confirmed supersonic run and the decision to shut everything down, less than 3 months passed. Sometimes budget cycles and procurement decisions move faster than engineers can document what they just proved. One more thing. The Leduc 0.22 is not just the end of a dead-end branch. It's a specific point where something became clear. A manned supersonic aircraft on ramjet power is possible, but uncontrollable fuel consumption and a narrow speed range make it unworkable as a combat aircraft. For missiles, ideal. For aircraft with a person on board, no. That line was drawn right here at Cazo Airfield in December 1957, and the aviation industry absorbed that conclusion very quickly. Thanks for watching to the end. If you're into aircraft like this, experimental, unconventional, often forgotten, subscribe to the channel. New videos come out regularly. A like on the video helps the algorithm push it further, and that genuinely matters for a small channel. And if you have something to say about Leduc or ramjet engines in general, drop it in the comments. I read everything.